So we'll continue on with our number theory section and talk about, again, some things that you probably have seen before in grade school, which is GCD and LCM. So these are actually well-solved problems in computer science and in discrete mathematics, and I'll show you why in a second. But you've probably heard of greatest common divisor and least common multiple in math before. So let's just officially define it once again. And according to the notation that we have, let's define it once again. So let A and B be integers, and A and B cannot be zero. Okay, so the largest integer d such that d divides A and d divides B is called the greatest common divisor. So the greatest common divisor. So it must be common. So the divisor must be common to both A and B, and it must be the greatest of the two. So for example, if I wanted to find the GCD of, let's say, 24 and 36, then we are looking for the largest d. Okay, so here we're looking for the largest d that is a divisor of both. So such that d divides 24 and d divides 36. So we can try out a few numbers and we'll find that the largest such d that fits this equation is 12. So it's 12 times an integer is 24, 12 times an integer is 36, and it is the largest of such values. All right, so this is just a reminder of what GCD is. We're actually going to solve it in 1 second. There are different ways that we can solve GCD, but we want to, in a second, compare two methods in order to find GCD. But before we do that, you'll often hear this term relatively prime. So integers A and B are relatively prime if their greatest common divisor is equal to 1. So this is probably one thing that we should revise, which is there always a GCD? Okay, so if I give you just two numbers, is there always a GCD? And the answer is yes, there will always be a GCD because there's always a number that divides both numbers. So here we can say that d, for example, no matter what the numbers are, if d is assigned to be 1, 1 will divide anything. 1 divides anything, right? Because again, remember, 1 times an integer is equal to the second integer. It's always true, right? Because 1 times that number is always the number. So when integers a and b have the greatest common divisor as 1, they are called relatively prime. Okay, so GCD of 10 and 17, for example, is equal to 1, and therefore we can say 10 and 17 are relatively prime. So just remember this as a definition, I guess, but we're going to see something a little bit interesting, I guess, about relatively prime numbers a little bit later on. We can say that the integers a1, a2, a3, all the way up to an are pairwise relatively prime if any pair of the numbers are all have the case that GCD of those pairs are equal to 1. So for example, I can do GCD, I can say 10, 17, and I don't know, 21 are pairwise relatively prime. Okay, so all of them have the greatest common divisor between any pair of numbers is always equal to 1. And you can just verify this. Also verify that for two numbers to be relatively prime, they themselves do not need to be prime numbers, right? So just verify 10 and 21 are not prime numbers, but they are part of a pairwise relatively prime set. Okay, so just remember this. These are just definitions for now, so we'll label this properly. So 4-9 and 4-11, or 4-10, and just remember these as definitions. All right. Now, on the other end, we have what's called a least common multiple, LCM. And again, you probably have heard of this term before in mathematics. We say that the least common multiple of two integers. Now, this time they have to be positive integers. So LCM is not defined on negative numbers. So two positive numbers, A and B. So it is the smallest positive integer that is divisible by both a and b. So this time we are talking about not the divisor, but the multiple. So maybe let's do another example here. So if, for example, we have the LCM of 70 and 20, so we are looking for the smallest m. So we're looking for the smallest multiple. So smallest positive m, such that 70 divides m and 20 divides m. So again, this is the multiple. So I think the largest, or sorry, the smallest positive number here is going to be 140. So you can just double check that. So 70 times an integer is 140, 20 times an integer is 140, and 140 is the smallest positive of those numbers. All right, so this is the LCM. Now, there are many applications that require GCD and LCM. I'm not going to go into the applications, but just know that these are well-solved problems in computer science. So there are lots of problems out there that require us to be able to find GCD and LCM really quickly in order to solve a bigger problem. So what is a good strategy or a good method in order to find the GCD or LCM? Well, it turns out that when we do prime factorization of numbers, it helps us really quickly to be able to determine GCD and LCM. So it turns out that when we do a prime factorization of A and B, that the GCD is just the smaller of the primes exponents, and the LCM are the larger of the primes exponents. Now, just to give you an example of what I mean by this, we have, let's say, A is equal to 120 and B is equal to 500. And let's say A, well, when we take the prime factorization of A, we get 2 cubed times 3 times 5. And then 500 is 2 to the 2 times 5 to the 3. All right, so if we wanted to find the GCD of 120 and 500, and we already have the prime factorization of the two, then you can see that we're going to take the smaller, the minimum of the primes. So we're going to compare 2 to the 2 and 2 to the 3. So 2 as a prime number to the 2 and 2 to the 3. 2 to the 2 is the smaller one, so I'm going to keep that. Now, I take a look at 3. So imagine this is 3 to the 1, and then we actually have a 3 to the 0. You can imagine we have a 3 to the 0, right? Because there is no 3 involved in the prime factorization of 500. So what is the smaller? The smaller is 3 to the 0. So I keep 3 to the 0. Again, for the 5, I have 5 to the 1 and 5 to the 3. I keep 5 to the 1. So the GCD, very quickly, the GCD of 120 and 500 is calculated to be 20. Similarly, I can do the same for the LCM. So LCM of 120 and 500 is going to be the larger of the two. So this time we take 2 to the 3, we take 3 to the 1, and we take 5 to the 3, and we have 3,000 as the LCM of those two numbers. Now, you might look at this and say, well, that's a really good strategy. That's really quick, right? All we need is the prime factorization, and then we can just look at all the prime numbers and then just decide which one is the smaller and which one is the larger, and we can find both at the same time. Now, notice also that it turns out that if we take the LCM and the GCD and we multiply them together, right, it ends up as being A times B. Well, I hope this is intuitive to you, because if you take A times B, you're basically taking all of these prime factorizations, right? 2 to the 3, 2 to the 2, 3 to the 1, 3 to the 0, 5 to the 1, 5 to the 3. We're taking all of those and multiplying it together. It just so happens that GCD, that each one of those prime factorizations belong to the GCD or the LCM. So I hope you can convince yourself that if I multiply these two numbers together, I get the product of A times B. And this is actually a really important result, because what I want to tell you next is that GCD, the way to find GCD in this situation, is very inefficient for a computer. Okay, so think about how I taught you to do prime factorization before. If I had the number 500, how do we do prime factorization? Well, we would do something like, let's think of two numbers that multiply to 500. So I can think of 10 and 50. And for us humans, this is actually pretty easy, right? Usually, because of our work with numbers, it's pretty easy to come up with two. And then we can prime factorize again until we hit a prime number. So here we have a 5 and a 10, and then 10 can be split into 2 and 5. And then there is our prime factorization. Now, try to teach this to a computer. In fact, try to teach trying to verify whether a number is a prime number to a computer. It's very difficult. Okay, so just to let you know, I mean, I know many of you don't have programming experience, but just trust me, if you wanted to program something to figure out whether or not a number that you give it is a prime number, it's actually a very difficult problem. Well, not difficult, but inefficient. It's very inefficient for a computer. It would have to check all the numbers beneath it in order to verify that it is not a prime, it is a prime number. So prime factorization, to go a little bit further than that, is a very expensive process for the computer. So if we were to teach a computer to find GCD and LCM, we would never do this. We would never teach the computer to do it in this way. But what if I told you that there's a very fast way to find GCD for a computer and for humans as well? All right. So what if I told you there's a very fast way to find GCD? Then, if I wanted to find the LCM, well, that's easy because now I can just take a times b and then divide it by the GCD, and then I will get the LCM. Okay, so really, I need a fast method in order to solve one of these two problems. And then the other one is going to be obvious. I just need to do some mathematical calculation, and then you'll have your answer there. Okay, so once again, this method of finding GCD and LCM is not that efficient. What we want to find out is some way to be a little bit more efficient with calculating the GCD. So in a few slides, we are going to talk about that method. We're going to take a little bit of a turn here, and we're going to talk a little bit about some tools that we're going to need in order to find GCD. So the first tool that we need is called modular arithmetic. So modular arithmetic simply means I take two numbers, I divide them, but instead of keeping the quotient, I only keep the remainder. Okay, so divide a by m, but only keep the remainder. This is signified by a mod m. So whenever you see a mod m, or in programming, it's typically a percent sign. So whenever you see a percent sign m, that is what we're talking about. So a divided by m, but keep only the remainder. So for example, if I take 17 mod 5, so 17 divided by 5 and keep only the remainder, the answer is 2 because 5 goes into 17 three times with a remainder 2. So the equation was something like this. 17 is equal to 5, remember, times q plus r. Remember that equation, that fundamental theorem of arithmetic from the previous video. So this is r, so we just keep the r. So notice that in this case, we don't care about the quotient at all. So is there a practical application for this? The answer is yes. There's many, many practical applications for mod. In fact, if you are to go on in programming, you're going to see many, many examples where we use mod as a calculation rather than the division. It's actually arguably more important to computer science than, than division. Let's give another example here. What if I had negative 133 and then I do a mod 9? And this is equal to 2. So negative 133 is equal to 9 times negative 15. So please verify my math here, plus 2. Now remember, once again, that the remainder has to be between 0 and d minus 1. Right, so if I'm dividing by 5, the remainder has to be 0, 1, 2, 3, or 4. If I'm dividing by 9, the remainder has to range from 0 up to 8. Okay, so just remember that. So mod means taking the remainder of the two numbers when I divide them. Okay, now there is a very nice application here, which I'm going to talk about in 1 second, but I'm going to talk about one other thing pertaining to mod, which is called congruency of modular arithmetic. Okay, congruency of modular arithmetic. So if a and b are integers and m is a positive integer, then a is congruent to b mod m if a divides, sorry, if m divides a minus b. So m divides a minus b. All right, so the notation that we use is we use a congruent, so this is a triple equal sign, and then mod m. So usually we write mod or modulo m to signify that they are congruent modulo m. So this means that m divides a minus b. So what's another way of saying this? M times an integer is equal to the difference of a and b. Okay, so a times an integer is equal to the difference of a and b. So in English, what does that mean? All right, so I'll talk about that in 1 second, but there is actually an alternative definition here. But let me just first give you an example. If I take 17 and 5, right, I can say that 17 is congruent to 5 modulo 4. Now, 17 minus 5 here is 12. So what we're really saying is that 4 divides 17 minus 5. So 4 divides 12, which is a true statement. Okay. Now understand that when we say A and B are congruent, the order doesn't matter. So if 17 is congruent to 5 mod 4, then so is 5 congruent to 17 mod 4. Okay, so we can say 4 divides 5 minus 17. So 5 minus 17 is negative 12. 4 times a number is, 4 times an integer is negative 12. Sure, that's true. Okay, so notice that the order here does not matter. The order of A and B does not matter. All right, so officially, our definition is M divides A minus B. Now, if you take a look at what 17 or how 17 and 5 are related to each other, they are related in that they are spaced for a multiple of 4 apart. Okay, so what do I mean by this? 5, 6, I'm just going to put all the numbers 8, 9, 10, 11, 12, 13, 14, and 15. So what this means is that if I make jumps of 4 at a time, I will be able to get from 15 up to 17. Sorry, 15. 5 up to 17. Okay, so once again, what does 4 divides 17 minus 5 mean? It means that if I start at 5 and I go in steps of 4, I will eventually get to 17. Okay, so 5, I go step of 4, 1, 2, 3, 4, here. I go 1, 2, 3, 4, I go here, 1, 2, 3, 4, I get to 17. Okay, so that's what congruency of two numbers mean modulo m. Okay, so once again, 17 minus 5, the difference between A and B is a multiple of 4. Okay, so that's officially what congruency means. Now, if we go further with this example, you might say, okay, so if they differ in jumps of 4, it must also mean that if I take 17 and take the remainder when I divide by 4, this must also be equal to 5 mod 4. So if you just verify this, 17 mod 4 is equal to 1, right? So 17 divided by 4, the remainder is 1. 5 divided by 4, the remainder is 1. So here's an alternative definition. So here's alternate definition. Alternate definition is if I have A congruent to B mod M, we can say A mod M is equal to B mod M. So just take this as definition number 2. So both of these are definitions. Okay, so you can say M divides A minus B. It's the exact same thing as saying A mod M is equal to B mod M. Those two are identical to each other. Okay, so with this in mind, let's do a little bit of an application. So this is actually a theorem that I think with the tools that we have, you are able to solve. So if you want a little bit of a challenge, you can pause the video and see if you can prove this. Now, before we do that, I'm just going to note that there is in this theorem an if and only if. And that means anytime we see an if and only if, it is a arrow, it's a biconditional arrow. So do you remember earlier in our proof section, when we need to prove biconditional, what do we need to do? Okay, so try to remember what we need to do for that. So there's a hint. And again, if you want to prove this right now, please try, pause the video and try to prove this. And then we will work together on this right about now. All right, so in the forward direction, we have the statement, let m be a positive integer. The integers a and b are congruent modulo m. So a and b are congruent modulo m. I'm going to start off with this. Okay, if and only if there is an integer k such that a is equal to b plus km. Now, the first thing we'll do is we're going to start in the forward direction. Okay, so if a and b are congruent, can I eventually claim that there is an integer k so that a is equal to b plus km? Okay, well, let's start going and see if we can actually get there. So we said earlier that one of the definitions for congruency is m divides a minus b. Right? That's one of the definitions. What is the definition of divides, the straight line? So remember, there is an integer k, so that m times k is equal to a minus b. That is the definition of divides. Okay, well, how do we get to this? Well, I think we just do a little bit of math. There exists a k so that b plus mk is equal to a. So I just move b to the other side, and I think that's it. That's really our whole proof. Okay, so now please notice that my argument up to this point is a one-directional argument. Okay, so I said a is congruent to b, implies that m divides a minus b, implies that there is a k, implies that the last statement is true. But please notice how we got to each step. The first step and the second step are definitions. The third step is math. Okay, so we need to ask ourselves, is it possible to make the same argument going the other way as well? And I think it is. So math, I can say this is a double arrow back to this. So I can move b back to the right-hand side and it would still be true. So this arrow, that last arrow really should have been a double arrow. This arrow, because it's a definition, should have been a double arrow. And this arrow also, because it's a definition, should have been a double arrow. Now, I do this to make a point because it's not always that we're so lucky. Okay, every single step also had a backward step that is identical to it. So it's not always this lucky. Okay, but I just want you to be aware that whenever we have an if and only if, whenever I'm trying to prove P if and only if Q, I always need to argue both directions. Okay, because this is a very special case. We got very lucky that every step actually goes both ways, but it's not always the case. Okay, so in fact, some of the proofs in your textbook, you'll find that the method for going, the proof for going one direction is very different than the proof going in the opposite direction. And in fact, we saw that earlier with the n is odd implies n squared is odd. The forward direction is very different than the backwards direction. So please keep that in mind. Okay, there is a theorem 5 here. So what I'm going to do is leave theorem 5 for you to figure out. But let me give you a strategy of how to prove theorem 5. So theorem 5, we have A is congruent to B mod M and C is congruent to D mod M. So those are the premises that we're going to start with, right? So this is basically your first step. So C is congruent to D mod M. Now, what do these mean, right? Well, what is the definition of these and where can we go from there? So what I would do in this theorem is I would make two separate proofs. So if these are your premises, can you conclude that A plus C is congruent to B plus D mod M? And then in a separate proof, can you prove that A times C is congruent to B times D mod M? Okay, so try to do them separately, and I think you have the tools to do this. In fact, it's actually very similar to the last proof that we did, but see if you can prove both of these. If you have problems, again, please come to the office hours. Please send me an email so that we can discuss it. But right now, I think you have enough to prove theorem 5. All right, so the last subtopic that we want to talk about in this section is called the Euclidean algorithm. And a Euclidean algorithm, again, is a very nice application. Okay, so it was this guy named Euclid, which is a very famous mathematician that came up with this process, and this is actually one of the applications of that process. So what we want to find out, or what we want to claim here, is that if we have a form, if a, b, q, and r are integers, and a is equal to bq plus r. Now, I hope that that form looks familiar. We'll talk about that in 1 second. And then the GCD of a and b is equal to the GCD of b and r. Okay, so if the GCD of A and B here is equal to the GCD of B and R if A and B and Q and R are related in this way. Okay, so let's see if we can prove this. And then we'll talk about what the application is. Now, what this is claiming is that the greatest common divisor of A and B is the same as the greatest common divisor of B and R. Okay. Now, what I'm about to prove is actually something a little bit stronger. I'm going to prove that every single uh, divisor of A and B is also a divisor of B and R. Okay, so every single divisor of A and B is also a divisor of B and R. So let's see if we can prove this. In fact, here is my statement that I want to prove. All divisors of A and B are also divisors of R. Okay, now let's take a simple example here. So let's say A is 36 and B is 24. Okay, now if I take 36 and I divide by 24 and I get the remainder, so notice that that is where it comes from. This is the division algorithm. Okay, so if I take A and divide by B and I come up with a R, so R in this case is equal to 12, then the claim is that every common divisor of 36 and 24 is also common to 24 and 12. So A and B have the same divisors as B and R. Now, if this is true, this is actually a very nice tool because we're claiming that 24 and 12 is actually a smaller problem than 36 and 24. So if the GCDs are in fact equal, then I really just shrunk the problem into something a lot smaller. So let's see if this is true. So if I have 36 and 24, what are the common divisors of 36 and 24? Well, we have 2, we have 4, we have 6, we have not 8. We also have 12. And is that it? So we have, oh, we have also 3. Okay, I think that's it, right? So I hope I'm not missing any. All right. So what are all the common divisors of 24 and 12? Well, take a look. It should be the same. So 2, 4, 6, 12, and also 3. 3 was what I was missing before. So just verify that, in fact, the divisors are all common. So this is what we want to prove. Okay. And again, if we are able to prove this, this is actually very nice. This is a very nice application. Okay. So the way that I'm going to prove this is to show that if we have a divisor D that divides A and D divides B, so if both of those are true, this implies that D also divides R. Okay, so this is essentially what we're trying to prove. Now, here is our premise. Our premise is D divides A and also D divides B. So can I get to eventually to be able to show that D divides R? Okay, so the first thing we should note is that if I have this equation, R is actually A minus B times Q. Okay, so I just moved B times Q over to the other side, right? So R is essentially equal to A minus BQ. So if D divides B, can I then say that D divides B times negative Q? Now, what is negative Q? Well, in fact, it doesn't matter. Q is just some integer, right? So if D divides B, then D divides B times anything. Remember in theorem one, so look back in theorem one of our chapter here. Under theorem one, there is a theorem exactly like that. If A divides B, then A divides B times anything. Okay, so this must be true. All right, similarly, from this fact and this fact, we can also say that D divides A plus B times negative Q. And why is that? Because we proved this earlier in theorem one. So again, take a look back at theorem one. There was a theorem that says if A divides B and A divides C, then A divides B plus C, right? So surely this is also true. And what is this right-hand side here? It's nothing more than R. So take a look. We have that A plus B times negative Q is nothing more than R. So what we've proven here is that if we have a common divisor of A and B, it will also be a common divisor to the remainder of A and B. Okay, so if we have a common divisor of A and B, it will also be a common divisor of the remainder and B. Now, notice what I said before. If I try to find the GCD of A and B, it's a large problem. So 36 and 24, that's a large problem. But if I have, I can say something a little bit smaller than that. So I can claim something a little bit smaller than that. And I can say that 24, this is equivalent to the GCD of 24 and 12, which is a smaller problem. Now, I think you know where I'm going with this. What I can do is keep dividing this, right, over and over again and getting the remainder over and over again until I get to such a small problem that I can look at it and solve it. Okay, and that is the strategy here. So once again, GCD of A and B, let's say A and B are very large numbers. Then I'm going to divide those two and find the remainder. B and R are in fact the smaller of the two numbers, so we've shrunk it into a smaller problem. And we can keep doing this, shrinking the problem into something smaller and smaller and smaller until we get to a point where we can solve the problem. Okay, let me give you an example of this. So this is what we call a Euclidean algorithm. So what I just explained is called a Euclidean algorithm. So the Euclidean algorithm solves GCD. So let's say I wanted to find the GCD of, let's see, 140, yeah, uh, uh, 414 and 248. Okay, I wanted to find the GCD of this, 414 and 248. So what the Euclidean algorithm is telling me is if I want to find the GCD of A and B, I can just divide these two numbers and then find the remainder. Okay, so I'm going to do that first. So take 414 and divided by 248. This is equal to times 1 plus, and then I believe the answer is the remainder is 166. Okay, so we have 166 as the remainder. I'll just label this R for now. Okay, so now we can claim that the GCD of 414 is equivalent to the GCD of 248 and 166. Right? So according to that theorem that we just proved, we've shrunk it into a smaller problem. Well, maybe this is still a large problem. So what do? Well, we can divide again. We can now take 248 and divide by 166, which is times 1 plus, I believe, 82. So please check my math. Okay. So now we can say this is equal to the GCD of 166 and 82. And you see how we're shrinking the problem every single time. So let's keep going. When should we stop? Well, 166 is equal to 82 times 2 plus 2. Okay, so now this is equivalent to the GCD of 82 and 2. So 82 divided by 2 is equal to 41 plus 0. And when we hit 0, we stop. Okay, so we just keep dividing, keep dividing, keep dividing until we get to the remainder 0. And we will always hit the remainder 0. Okay, now when we hit the remainder 0, what is the GCD? Well, think about the last problem that we solved, right? We were looking for the GCD of 82 and 2. Well, 82 and 2 divides evenly, right? So 2 divides 82. So which one is our GCD? Well, it must be 2. It must be the smaller of the two numbers. So the answer is always the very last remainder that we have. So the GCD here is equal to 2. See, the answer is equal to 2. Okay, so once again, the strategy of the Euclidean algorithm is that we keep dividing, get the remainder, keep dividing, get the remainder until we get the remainder equal to 0. That will always happen. And then I take the GCD, which is equal to the last remainder. Okay, because when it hit 0, it would mean that the very last division that I made was had no remainder, which means it divides each other. Okay, so now there is a very nice application to this. So I hope everyone is able to understand the process of the Euclidean algorithm. Okay, so there's going to be a couple of examples that I put in the problem set that will allow you to practice it. But there's a couple of applications that come directly from the Euclidean algorithm. So it turns out that the GCD of two positive integers, a and b, can always be expressed as a linear combination. Okay, now what a linear combination means is that let's say I give you the number a and b. Okay, x and y are integers. Okay, so x and y are integers. I will always be able to fit some integer x and some integer y so that a and b are this will equal to the GCD. Okay, now I'll show you how to do that in 1 second. And in fact, we need to go back to the previous example. Okay, so the theorem goes like this. If a and b are positive integers, then there exists integers x. Now, integers could be negative, they could be positive. They exist x and y such that the GCD is equal to ax plus by. Okay, now there's a second lemma that comes from this, but I'll get back to that in 1 second. But let's figure out how to get this x and y, right? So how is it that this x and y can appear? Now for this example, I'm not going to prove this theorem. So I'm not going to prove theorem 7, but instead I'm going to show you how to find the x and y. So hopefully you would be convinced that any a and b that I give you, you would be able to find this x and y. Okay, so I'm going to go backwards here. So you notice that we said that the GCD of 414 and 248 is 2. Okay, so the GCD of 414 and 248 is equal to 2. So it turns out that 2 is equal to 166 minus 82 times 2. So this is well, let's do it this way. I think for readability, 2 times 82. I just moved this over to the other side. Okay, and now I can go backwards and I can figure out what each one of these statements or which these numbers are. So I'm going to go back and check out 82. So if I take 82 is equal to 248 minus 1 times 166, I'm going to plug this 82 into here. Okay, and I'm going to get the following. 166, oops, 166 minus 2 times, and I'm going to plug this equation in there, 248 minus 1 times 166. Okay, so if we do a little bit of math, it turns out that this equals 3 times 166 minus 2 times 248. Now, please just check my math on this, just to convince yourself that this is the right number. And now let's take a look at 166. I'm going to go back up here and I'm going to say that 166 is equal to 414 minus 1 times 248, and I'm going to plug that into 166. And I'm just going to keep doing this until my whole equation only involves 414 and 248. So let's do a little bit of math here. We get 3 times 414 minus 1 times 248, and then minus 2 times 248. So I just plugged in the 166 in there. And then again, we do a little bit of math. We will find that this is equal to 3 times 414 minus 5 times 248. Okay, so if you take a look at this example, the GCD of the two, the GCD of 414 and 248 is equal to 2. That GCD can be written in the linear combination. So this ends up to be our x, this ends up to be our y. Okay, so we can write that the GCD of 414 and 248, which is 2, is equal to x times a minus plus y times b. So this is our a, this is our b. So I hope you can see where that equation is coming from. And by the way, I hope you can see that the process that I used will work no matter what, because all we're doing is kind of unpackaging the Euclidean algorithm, right? So as we went through the Euclidean algorithm, they were all integers, right? Everything that we were dealing with was integers. If we unpack this, it will always work out to be integers. The x and y will always work out as integers. So that is essentially where theorem 7 is coming from. Okay, so we had ax plus by is equal to the GCD of a and b. All right, so there is a lemma that comes from this theorem. Okay, so the lemma goes, if a, b, and c are positive integers, okay, a, b, and c are positive integers such that GCD of a and b is equal to 1. Okay, now this part is very important. Then and a divides BC, then A will divide C. Okay, now you might be saying, where is this coming from, right? How are those things even related? Well, it comes directly from this theorem. So let's start with this. We have premise number 1 and we have premise number 2. Okay, so I'm going to prove that if premise number 1 and 2 are true, then the conclusion must also be true. Okay, so let's write down our premise. So GCD of AB is equal to 1, and A divides BC. All right, so if the GCD of A and B is equal to 1, then that means there must exist x and y. So there has to exist x and y so that ax plus by is equal to 1, because that's what the theorem is telling me, right? So this is the GCD of A and B is equal to 1. So there must exist x and y so that this is true. We also know that A divides BC. So what I'm going to do here is multiply the both sides of this equation by c. So axc plus byc is equal to c. All right. So we know that A divides BC, right? So we know from this fact that A divides BC. So we also know that A divides BCY, and that's where this comes from. Okay, so we know that A divides BCY. Okay, we know that A divides AXC. And how do we know that? Well, because A is part of this, right? So we know that A divides A. We know that, right? And therefore, A divides A times anything. Okay, so we can say A divides this and A divides this. So therefore, A must divide the addition of the two. And again, this is from theorem 1. Okay, and what is AXC plus BYC? Well, it's C, right? Because from this, we can see that this is equal to C. So there we go. There is our conclusion here. And this is a very nice proof, right? This is a very straightforward proof. This is once again an application of the direct proof. Okay, now I don't really have an application for this last lemma, but the the theorem of the linear combination is again a very nice result in computer science. There's a lot of applications using the Euclidean algorithm and using GCD and so forth. Okay, so I hope this part has been helpful. So take a look back. We did talk about a lot of different things, a lot of different definitions for number theory. What I would recommend if you're studying for this on for a quiz or an exam or anything like that, um, know the definitions. Okay, so it's I think it's less important, although it is you should know what the theorems are, but know the definitions because most of those theorems come from the definitions themselves. Okay, so know the definitions. What is division? What does the divide symbol mean? What does mod mean? What does congruency mean? So know all of those things, because then you'll be able to figure out what the problems are asking. Okay, so I think this is going to end off our topic on number theory. So I will see everybody in the next video.